RMO 2024. Problem 1. Let n be a positive integer greater than 1. We define a special property called nice for rearrangements of the set 1, 2, up to n. A rearrangement A1, A2, up to n of the numbers 1 through n is called nice if the following condition holds for every k. From 2 up to n. The partial sum A1 plus A2 plus plus AK is not divisible by k. In other words, for every k from 2 to n, when you add up the first k terms, the result is never a multiple of k. Let's see examples of nice rearrangements to build intuition. Take n equals 4, so we arrange 1, 2, 3, 4. Consider the rearrangement 2, 1, 4, 3. Check k equals 2, sum of first two terms is 2 plus 1 equals 3. Is 3 divisible by 2? No. Good. Check k equals 3, sum of first 3 is 2 plus 1 plus 4 equals 7. Is 7 divisible by 3? No. Good. Check k equals 4, sum is 2 plus 1 plus 4 plus 3 equals 10. Is 10 divisible by 4? No. Good. So the rearrangement 2, 1, 4, 3 is nice for n equals 4. Now let's see a rearrangement that is not nice. Take n equals 4 again. But use the arrangement 1, 2, 3, 4. Check k equals 2. The first two terms sum to 1 plus 2 equals 3. Is 3 divisible by 2? No. That's fine. Check k equals 3, sum is 1 plus 2 plus 3 equals 6. Is 6 divisible by 3? Yes. 6 equals 3 times 2. The condition is violated at k equals 3. So 1, 2, 3, 4 is not a nice rearrangement. This shows that not every arrangement is nice. We need to choose the order carefully. The problem has two parts. Part A asks, if n is odd and greater than 1, prove that no nice rearrangement of 1 through n exists. This means no matter how you shuffle 1 through n, the nice property will always be violated for some k. Part B asks, if n is even, explicitly find a nice rearrangement of 1 through n. We need to construct the specific sequence and prove it works. Together these two parts completely characterize which values of n admit a nice rearrangement. Here is the complete official problem statement. Let n greater than 1 be a positive integer. Call a rearrangement A1, A2, up to n of 1, 2, up to n nice if for every k equals 2, 3, up to n. The sum A1 plus A2 plus plus AK is not divisible by k. Part A. If n greater than 1 is odd, prove that there is no nice rearrangement. Part B. If n is even, find a nice rearrangement of 1, 2, up to n. Let's now prove both parts step by step. Part A. Proving no nice rearrangement exists for odd n. We use a proof by contradiction. Assume for the sake of argument that A1, A2, up to n is a nice rearrangement of 1 through n, where n is odd. Since it is nice, the condition must hold for every k from 2 to n. In particular, it must hold for the specific value k equals n. This means, the full sum A1 plus A2 plus plus n must not be divisible by n. Now here is the crucial observation. The sequence A1, A2, up to n is a rearrangement of 1, 2, up to n. That means the values are exactly the same set, just in a different order. Therefore the total sum A1 plus A2 plus plus n equals 1 plus 2 plus plus n. Which by the well-known formula equals n times n plus 1 divided by 2. Now, when n is odd, n plus 1 is even. So n plus 1 divided by 2 is an integer. This means n times n plus 1 divided by 2 is divisible by n. So the full sum is divisible by n. Now we have our contradiction. We assumed the rearrangement is nice, which requires the full sum to not be divisible by n. But we just proved the full sum equals n times n plus 1 over 2, which is divisible by n when n is odd. These two facts cannot both be true at the same time. This contradiction shows our assumption was wrong. Therefore, no nice rearrangement of 1 through n exists when n is odd. Part A is proved. Part B. Constructing a nice rearrangement for even n. Let n equal 2 meters for some positive integer m. The construction is elegant. Simply swap each consecutive pair. Take the sequence 2, 1, 4, 3, 6, 5, and so on, ending with 2 meters. 2 meters minus 1. In other words, write all even numbers in order. But each even number is immediately followed by the odd number 1 less than it. For n equals 6, the sequence is 2, 1, 4, 3, 6, 5. For n equals 8, the sequence is 2, 1, 4, 3, 6, 5, 8, 7. Now we must prove this construction is always nice. Now we verify the construction is nice. We check two cases. Case 1, k is even. The first k terms are 2, 1, 4, 3, up to k minus 1. This is exactly k over 2 full pairs. The sum of each pair 2i plus 2i minus 1 equals 4i minus 1. Summing over all k over 2 pairs gives k times k plus 1 over 2. Case 2, k is odd. At least 3. We have taken k minus 1 over 2 full pairs plus 1 extra term. The kth term is the even number k plus 1. The first k minus 1 terms sum to k minus 1 times k over 2. Adding the kth term gives k times k plus 1 over 2. Plus 1. This is exactly 1 more than a multiple of k. So it is not divisible by k. The odd case is verified. So both cases are verified. For k even, the partial sum equals k times k plus 1 over 2, which is not divisible by k because k plus 1 over 2 is not an integer. For k odd and at least 3, the partial sum equals k times k plus 1 over 2 plus 1, which is 1 more than a multiple of k, so also not divisible by k. Therefore the sequence 2, 1, 4, 3, 6, 5, up to 2 meters. 2 meters minus 1 is always a nice rearrangement for any even n equals 2 meters. Part B is proved. Here is the complete solution summary. A nice rearrangement of 1 through n exists if and only if n is even. For odd n, the total sum is always divisible by n, contradicting the nice condition at k equals n. For even n, the sequence 2, 1, 4, 3, 6, 5, up to n minus 1 works, as verified by checking even and odd k separately.